Hello everyone, welcome to NotebookOps, a pattern for building notebook-centric data platforms. Perhaps a better title would be How to Build a DIY Analytics Platform Using Open Source Tools. Today, I'll talk about my experience from helping set up such a platform at Grofers, which is one of India's largest grocery delivery services. A little bit about me, I'm Vinayak, a software engineer currently living in New Delhi. I maintain Camelot and Excalibur, two tools that can help you extract tables from PDFs. You can check them out at this link. Right now, I'm in the Fall 1 batch at the Recurse Center, which is a self-directed educational retreat for programmers in New York City. At RC, I'm working towards becoming a better programmer. Back to the talk. For the past few years, we've been seeing this growing trend of enterprise notebook infra. It has been a recurring theme at every JupyterCon, including this one. Every data engineer that I've talked to has worked on or is working on setting up some kind of a notebook infra at their organization. This quote from Brian Granger sums it up pretty nicely. He says that we are entering an era where large complex organizations need to scale interactive computing with data to their entire organization in a manner that is collaborative, secure, and human-centered. He further adds that there is an organizational shift from the historical usage patterns of Jupyter being used by individuals in an ad hoc manner to the new world of large-scale Jupyter deployments. At JupyterCon 2018, Paco Nathan also pointed out how large organizations are adopting Jupyter at scale. He says that on the one hand, there are people in the organization who are well trained in the problem, the domain experts. They may not have the technical expertise at first, but they can use Jupyter to gain enough of the tooling to really amplify what they're doing in the domain. This is also called citizen data science, where enterprise notebook and infra makes it easy for anyone in the organization to get access to data and do wonderful things with it. Also, on the other hand, there is the fresh graduates that these organizations are hiring. And since they already know how to use Jupyter because of their coursework, enterprise notebook infra can help them deliver results from the first day itself. Over the past few years, we have seen multiple talks and blog posts from large organizations like PayPal and Civis Analytics around this theme. But perhaps the most famous of all stories is of Netflix, where they've set up a DIY data analytics platform by putting notebooks at the core. In their platform, anyone can launch a notebook server on demand. Users can also choose resources like CPU and memory, after which their server gets launched in a container using Titus, which is their container management platform. And if someone wants to schedule their notebook to run at specific times, they can do so using Meson, which is their internal workflow orchestration platform. In a notebook-centric data platform, everything is a notebook. You want to write an ETL? Notebook. You want to train a model? Notebook. You want to send out a daily report? Believe it or not, notebook. Let's go back to 2019. In February, I joined Grofers as a data engineer in the Bangalore team. This is what the data team looked like. We had around 15 data analysts and around 5 data scientists. And the data team was supported by 3 data engineers, including me. Everyone in the data team was using JupyterLab. By that, I mean that we had one large EC2 instance set up, which was running JupyterLab and serving everyone. When something didn't work on this big instance, they would move to using JupyterLab on their laptops. Read credentials for various databases were often seen hard-coded inside notebooks, from where they would eventually land up in GitHub. And when someone in the data team wanted to schedule their notebook to run at a specific time, one of the engineers would use nb-convert to turn the notebook into a Python file and then schedule it as a cron job on the same EC2 instance. These could be notebooks that do ETLs or send out reports every morning. We also had an Airflow instance running on another EC2 for when someone in the data team wanted to run complex workflows where they wanted some dependencies between tasks. Let's discuss some of the problems in this whole setup. With one JupyterLab serving many users, there was no concept of a user session. One person's large workload could disrupt other users on the same system. This led to the other user moving to a JupyterLab on their laptop, which meant that they had to figure out a way to transfer their work from the server to their laptop. When one user upgraded a Python package on the server, the package would get upgraded for everyone, which would sometimes break another user's workflow. It was also a pain to keep the dependencies on the JupyterLab and Airflow instances in sync. And because of the dependency mismatches and a user constantly moving their work between the server and their laptop, it created a works on my machine problem. This also made it hard for another person to build on past work, because even if they were able to somehow find an old notebook, they wouldn't know the dependencies required to run it. And when someone in the data team wanted to schedule complex workflows, they wouldn't be able to do that themselves unless they were familiar with Airflow's Python API. This added a dependency on a data engineer to translate their notebook's core logic into Airflow. Over time, this approach put a lot of maintenance burden on the data engineers. This also added another dependency for when someone in the data team needed to debug why their workflow was failing on Airflow. Over time, Grofers has built a DIY DevOps culture where anyone can provision new infra resources and create Jenkins jobs very easily. There are dedicated infra and CI teams that have set up awesome tooling for this. Around the time we were facing the problems I just mentioned, the infra team set up a Kubernetes cluster, and there was an org-wide move to migrate services to Kubernetes. Anyone could install anything on the cluster once they had set up the required tooling. During that time, we in the Bangalore data engineering team started to think about how we could solve all the problems the data team was facing, using the infra and CI tools that we had at our disposal. These are Deepu and Sangarshan and my awesome teammates, and going forward, I'm going to be talking about all of our collective work. We knew about the notebook-centric platform Netflix set up from all the blog posts and talks they put out in 2018, so we had a general idea of what the state of the art looked like. But since some of the things in there weren't open source, we started looking for alternatives. And we found these tools, some of which we were already using. We decided to use Kubernetes in place of Titus for container management, JupyterHub in place of Interact as a multi-user notebook environment, and Airflow in place of Meson for workflow management, with some GitHub and Jenkins automation as glue to tie the JupyterHub and Airflow instances together. Let's talk about each of these components in some detail. JupyterHub is an awesome multi-user version of JupyterLab, which is designed for large user groups. The Jupyter team has written great docs on how you can set up JupyterHub on Kubernetes, where each user can spin up their own JupyterLab environment in an isolated Kubernetes pod. JupyterHub is famously used to serve more than 1,000 students in the Foundations of Data Science course at UC Berkeley. If you already have a Kubernetes cluster, it is pretty easy to set up JupyterHub using Helm. You just need to create a config in which you declare all of the settings that you need. For example, you can configure how someone logs into JupyterHub with a bunch of different methods. We used Google OAuth, which meant that everyone with a Grofers.com ID could access the whole platform using JupyterHub. And we used AWS's EFS to store everyone's files. Using EFS, every user would get a brand new file system which would be mounted on their JupyterLab server at /home/jovial. Anything that they created would be persisted on EFS at home/their username, and whenever they shut down their server and launched it again, the same EFS path would be mounted again. If you are wondering who Jovian is, it's just the name of the default user that shows up in Jupyter Docker images. In science fiction, a Jovian is an inhabitant of planet Jupyter, and in reality, it refers to Jupyter users like ourselves. You can reuse a bunch of Docker images that the Jupyter team maintains to create different environments for your users. For example, you can use a data science notebook Docker image, which contains all of the commonly used data science libraries, and create a new image out of it. You just need to import it at the top of your Docker file and then add commands to install all of your own libraries. We also did that and pushed the built images to our Docker registry. And after you built on top of an existing Docker image and pushed it to some registry, you can just list that image as one of the profiles in your config. All of the pre-built images that you list in the config show up like this when someone is looking to launch a server. You can also modify the existing form template to let users select the CPU and memory for their environment. And when the user clicks on start, they get their own JupyterLab running in an isolated Kubernetes pod. These environments remain the same across all users, which ensures reproducibility in the work that they do. For users logging in for the first time, we added a README notebook where they could give in some details like their name and email, and execute cells one by one to get SSH and GPG keys, which they could then add to their GitHub account. This made sure that they were able to clone and create repos inside the main org account, and also made sure that all of their commits were verified. We also built an internal Python library which automated some common tasks that everyone would do, and then added it to all the environments. One of these tasks was getting connections to databases within the org. So we added a function called getConnection, where any user could just pass in a simple connection ID to a database, get a connection, and make a query on the database. All IDs were listed in the README from earlier, and this solved the problem of hard-coded credentials inside notebooks being pushed to GitHub. The library also had other functions for some other common tasks, like sending emails, storing and retrieving files from S3, and creating tables in our data warehouse. All of this was adopted very quickly, as that was much simpler than everyone's earlier workflow. Let's talk about culling. JupyterHub has this nice feature where it can terminate or cull inactive user pods. This helps to scale everything down when resources aren't in use. You can set an inactivity time period after which a pod should be terminated. We found that this feature would cull user pods even if they left JupyterLab open in a browser and context switched to another task. This would usually happen when they were running a big task like training a model or running a large query. And it was painful for them when they came back and saw that the long-running task didn't complete because their server was no longer there. To overcome this, we used another JupyterHub feature called named servers, where you can launch a server and also give it a nickname. We modified the culling behavior to ignore pods that were launched with the LLAP suffix in the nickname, where LLAP stands for live long and prosper. And whenever we released a new version of the toolbox library, we built all the Docker images again, pushed the new images to our registry, and upgraded the JupyterHub deployment on Kubernetes. That made sure that everyone got the latest goodies when they launched a new server. And this did not affect users with running servers. They would just get the new environment when they relaunched their servers. Now that we had ensured a consistent and reproducible experience with JupyterHub, the next question was, how do we replicate the same experience for scheduling notebooks while also making the scheduling process very easy? At this point, we still had Airflow running on an EC2 instance, but the data team had grown and there were more users on the platform who wanted to schedule notebooks. That amplified some of the problems we saw earlier, and it started becoming difficult to scale and maintain Airflow on one EC2 instance, with the additional dependency on authoring and debugging workflows. Before we go further, let's briefly look into what Airflow is. Airflow is a platform where you can create and monitor workflows. You can think of it as a powerful cron. It has a simple Python API that lets you define workflows as DAGs, or directed acyclic graphs. It also comes with a lot of operators that let you define individual tasks inside your workflow. Let's see how we can define a DAG in Airflow. So each tag is a Python file where you import the DAG class and instantiate a DAG object with some metadata about the DAG, like the DAG ID, the owner, the date from which it should start running, and how often it should run. You can then import one of the bazillion operators. Here we import the Python operator, which lets you create a task to run any Python function. We then instantiate some task objects with this operator, and as you can see, each task is an ID, the Python function that it should run, and the DAG to which it belongs. And finally, we can define the dependency between tasks like this. Airflow comes with a nice web interface where we can see what the DAG looks like. This interface also shows you all the times the DAG is run, the status of each run, and the status of each task in that run. You can also click on individual tasks to view all of their logs. There's also a DAGs view where you can see a high-level status of all the DAGs running on your Airflow instance. Airflow also has a concept of executors which define how and where your task will be executed. You can execute tasks using Dask or Celery, and also configure the executors to run on a single server or in a distributed setup. Around the time we were working on solving some of the problems I mentioned earlier, we heard about the Kubernetes executor, which was shiny and brand new at that point. It can let you run each of the tasks in your DAG in their own Kubernetes pod. And to do that, you just need to define an executor config inside your Python DAG file with the Docker image that you want your task to run with. You can also define some Kubernetes specific things like the CPU and memory resources for the task pod. And after that, you can just add that executor config to your tasks like this. And just with this small change, all your DAGs become Kubernetes compatible, where each task in the DAG runs in its own Kubernetes pod. But how does Python operator relate to notebooks? Let's get back from the Airflow digression. And let's look at Papermill, which is an awesome Interact project built for configurable and reliable execution of notebooks. It lets you execute your notebook and save the output in another notebook, which can either go to S3 or any other object storage. You can also add a parameter stack to a cell and configure Papermill to inject inputs at runtime. Papermill just tags another cell after this tagged cell, thus overriding the variables in the earlier cell. This is super powerful for running notebooks in production. Last year, Airflow also added support for the Papermill operator, which means that combined with the Kubernetes executor, you can execute your notebooks in a Kubernetes pod using Papermill and then save the output notebook to S3. Airflow also has this powerful concept of macros, which can become input parameters to Papermill in the Papermill operator itself. For example, you can create a nice file hierarchy for output notebooks on S3 by specifying the DAG and run IDs in the Papermill output path. And if you're doing something like incremental loads in your notebook to backfill data into a sync table, you can specify the start and end date for your source SQL query as Airflow macros, which Airflow will pass to Papermill at runtime based on the date on which the DAG runs. Finally, you get a notebook DAG, which executes the notebook in a Kubernetes pod using Papermill with the image and resource requirements you provided, and then saves the output notebook to S3. We also configured Airflow to send alerts on Slack whenever a notebook failed. The alert would tag the DAG owner and also have a URL for the output notebook on commuter. And once a day in the morning, we would also send an automated email to every DAG owner with a short summary of the notebook run stats for the past day. And like I just mentioned, we set up Commuter, another awesome Interact project, on the S3 bucket where we were saving the output notebooks from Airflow. This was really helpful to look at notebooks when they failed. Airflow also shows you the logs on why a notebook failed, but the Commuter UI, where someone can look at the full output notebook and go to the cell that failed to look at the exact error, is a much nicer experience than looking at large logs on Airflow. One thing that you might want to think about with the KubernetesExecutor is how you deliver DAGs to your DAGs folder, which is where all the Python DAG files are kept. On one server, all Airflow components can see the DAGs folder because they share the same file system. But in a distributed setup like Kubernetes, there are 3 ways you can go about it. 1, have a sidecar container in all the Airflow pods that regularly pulls new DAGs from a Git repo. 2, build the DAGs into the Airflow Docker image itself, which can then be reused across all Airflow pods. Or 3, have a way to push new DAGs to a network file system, which can be mounted on all Airflow pods. We had a GitHub repo where we maintained all our DAGs, but we went with a third way because we already had a network file system, EFS, that we were using for JupyterHub. We didn't go the second way as we didn't want to build a new Airflow Docker image every time someone added a DAG, since that was happening quite often. And like JupyterHub, you can install Airflow on your Kubernetes cluster with Helm. This command uses the Airflow Helm chart from the stable Helm repo, but the Airflow community is soon coming up with their own official Helm chart, so you can keep a lookout for that. So with the Kubernetes executor, we had a way to execute notebooks reliably by running them in the same environment they were written in, because we were carefully maintaining the Docker images for both the JupyterHub and Airflow deployments. The next question was, how do we make authoring DAGs easy for anyone? We didn't want to stop anyone from scheduling their notebooks just because they weren't familiar with Airflow's Python API. So we came up with YAML DAG definitions, where any user could declare some DAG metadata using YAML and not care about writing a Python DAG file. Since most of the DAGs looked similar, we created Jinja templates for each type. Single notebook DAGs were the simplest, as they needed just one paper mill operator. And based on the DAG metadata a user provided, we would generate the final Python DAG file by rendering the Jinja template with the YAML values. But this still required a user to first write the YAML and then build a DAG file, and then also learn Git in order to push all the files to the DAG's GitHub repo we maintained. And that's where GitHub and Jenkins come in. We cloned and automatically updated the DAG's GitHub repo using pod hooks every time someone launched their JupyterLab server. When a user wanted to schedule their notebook, they could just go into the clone directory and create a new notebook project using a CLI tool that we baked into the environment. They could then just write some DAG metadata, like their name and the scheduling information, and copy their notebook into the project and push it to GitHub with this simple command. This would open a pull request against the DAG's GitHub repo. The workflow looks like this. A PR is raised by adding the YAML in notebook. This triggers a Jenkins job to render the Python DAG file. The job pushes the rendered DAG file back onto the pull requests branch. And additionally, the job does some other things, like checking for missing fields in the YAML, validating existing fields, checking for syntax errors in code, formatting the code, and finally adding a comment to the pull request with the build status. Before the pull request could be merged into the main branch, we also required a review from someone else in the same team. And when no reviewer was available, one of the data engineers would review the PR and merge it. And after the pull request was merged, a deploy job would push the new DAG to the EFS volume that was mounted on all Airflow pods. And that's how we enabled everyone to schedule a notebook that they wrote very easily. Today, this workflow is used by every data analyst and scientist and a lot of people in non-data roles across both of our offices in National Capital Region and Bangalore. These are some types of workflows that people have built. Notebook ETLs that load data into tables in Redshift, a data warehouse which powers our Tableau dashboards. Notebooks to send reports to various people inside the organization if some condition on some table is not met. Notebooks to train machine learning models on new data every day and load predictions in a table that's used by a consumer-facing system. And also very complex notebook workflows where multiple notebooks run in parallel to calculate the stock of items in different warehouses, with one final notebook calling the API for a downstream system that sends relevant orders to replenish the warehouse stock for the next day or week. Let's go through some of our learnings from setting all of this up. Always pin dependencies in all of your requirement.txts and Docker files. Initially, we were using the latest tag on the data science Docker image, but this one time, after building all the images and updating the JupyterHub Kubernetes deployment, every user would see an error when they tried to launch a new pod. It took a long time for us to figure out that the new version of the image broke some old kube spawner behavior that we were depending on. Pinning dependencies also helped us move quickly when we had to migrate from our old Kubernetes cluster to a new one. We just installed the Helm chart with the same config values, pointed the domain name to a new IP, and no user felt that some migration had taken place, since for them it all worked exactly the same. You should actively monitor this whole system using Prometheus and Grafana. It can help you get relevant metrics to improve user experience and also help in resource planning. After we started monitoring the resource usage for our JupyterHub deployment, we found that we could fit the same number of users on half the nodes, which helped us reduce cost. This one time, a user accidentally deleted their notebook, which contained all the work they'd been doing for the past 1 week. Yes, they should have pushed it to GitHub, and no, we somehow didn't find it in notebook checkpoints. But we were able to find the notebook in the latest EFS backup. Another time, an engineer accidentally reset the Airflow metadata database, on which the Airflow scheduler has a hard dependency, but we were able to quickly restore it from the latest RDS snapshot. You can also make some improvements on top of this setup. For new users, the graphical interface is much better than a CLI. New users shouldn't have to pay the command line tax and learn new tools like Git to work with data on the platform. Though Git is a powerful tool to learn, it shouldn't be forced upon anyone to do their work. A new project to check out in this space is Elira, which gives you this cool visual editor where you can drag and drop notebooks and build complex notebook pipelines. It also gives users a nice interface to review changes made to notebooks. And in a notebook-centric data platform, notebooks should become first-class citizens like tables, so that it's easier to discover them and build on past work. You can check out Amundsen to build a searchable catalog for your notebooks. I hope this was a nice intro to how you can use open source tools to build a notebook-centric data platform. And I hope you also learned about some problems that you can solve early in the process and some improvements that you can make. All of the docs related to this talk, like the Helm configs and the commands, will be available in this GitHub repo. Thank you for listening. If you're looking for a software/data engineer to join your team, or if you just want to chat about how awesome Jupyter notebooks are, you can reach out to me on Twitter at vortex_ape or using the contact information on my website. Lastly, I want to give a huge thank you to the JupyterCon team for everything they've done to bring this conference online. See you all next year.